For the second round of Zoom interviews, I'm going to show you a problem with some forces involved. And the first thing that you have to do is tell me how to draw the free body diagram. So I'll be drawing on the iPad and screen sharing with you. So you'll tell me how to draw the arrows and how to label them. And then you'll tell me how to take that free body diagram and turn it into the Newton's second law equations. Okay, so let's start with this example. We have these two forces that are acting on a single object. One of them is at an angle, and we're told the friction is present and the object is moving to the right. Okay, so we need to draw the free body diagram. Okay, so this is one type of problem that you may be asked, which is a single object with multiple forces acting on it, and probably one of those forces will need to be broken into components. All right, so I'll go ahead and draw the free body diagram. So you'd say there's a force 1 that points up and to the right. There's a force 2 that points to the left. There's a force of gravity that points down. There's a normal force that points up. And then there's also a force of friction that points to the left. And that's going to be a force of kinetic friction. Okay, so now I've incorporated all of those. Okay, so then I would say, okay, now how do you make your Newton's second law equations? So for each object, you can have Newton's second law equations in the x direction and the y direction. Right, so using the standard axes there, let's start with F net in the x direction. Right, so we're going to have F1, the x component only, points in the positive direction. Oh, I just saw that I got ahead of myself. I called that F sub n. That's actually F sub 2. Pointing to the left. Okay, so we've got F1, only the x component, then that's positive, so then we're going to do minus F sub 2 and minus the force of friction. And then it's not an equation until I set it equal to something, and that's the mass of the object times its acceleration. Okay, we don't know what that is, but we could solve for it. Now, we should go a little bit further and show how to break down this F1x into its components. That's going to be F1 times the cosine of theta, because that's the adjacent side of that angle. So F1 cosine theta, we're going to have minus F2. And then we also know that the force of friction is equal to mu sub k times the normal force is equal to ma. Okay, so if you don't go ahead and do it yourself, I'll probably prompt you on taking telling me how to use trig to break that force into components and how we can relate the force of friction to the normal force. Okay, and then F net in the y direction is we've got the normal force points up. We've also got a positive y component of F1, and then the force of gravity points down. And then that is equal to the mass of the object times the acceleration in the y direction, but the object is not moving in the y direction, so that is 0. Right? And then the one additional step of breaking this force into components, that's going to be F1 sine theta, and then the force of gravity we can always write as the mass of the object times g, and that's equal to 0. Okay, so now we have the two net force equations for the object, and if this were a homework problem or a written exam problem, you could solve for whatever's unknown, but that's as far as I'm asking you to go for this interview. Right, so be able to tell me how to draw that free body diagram, and then take that free body diagram and convert it into Newton's second law equations. The other option that you might have is a case where you have multiple objects. So here we have a pulling force that is pulling on that first penguin, and that first penguin is tied to the second penguin. So they're actually labeled as M2 and M3. So let's say we'll draw the free body diagram for this penguin. That's going to be, it's going to have some force of tension pulling to the right. It's going to have a normal force pointing up and a force of gravity pointing down. Now I should really label these. Okay, so that's penguin 3, so I'll label that normal force 3 and force of gravity 3. And then there's also going to be a force of friction. Again, need to label that with a 3. And then for the other penguin, we've got normal force again, force of gravity. We've got the pulling force from the hand. We've got the force of tension, and there's a force of friction on this one, which is different from the other force of friction. And then you should be able to tell me that these forces of tension are Newton's third law pairs. Right? So there's always going to be one Newton's third law pair, so you should be prepared to point that out. And that tension is the same because they both refer to that rope that connects the two. Okay, and then for each of these, we're going to have net force equations. So if we start with penguin 3, then the net force in the y direction for penguin 3 is normal force minus the force of tension, and that is equal to 0 because the penguin's not moving. Oops. We've got the normal force and then minus the force of gravity. That's equal to 0 because the penguin's not moving in the vertical direction. F net x is the force of tension is in the positive x direction, and the force of friction is in the negative x direction, and that's equal to m3, because that's the mass of that penguin, times its acceleration. And then for penguin 2, I've got F net in the y direction, looks very similar. We've got a normal force and a force of gravity. And then in the x direction, we've got a pulling force, which points to the right, so that's positive. The force of tension points to the left. That's from the rope that connects the two penguins. And then also a force of friction, which points to the left, and that's going to be equal to m2a. Right, and then I'm not going to ask you to do any algebra with those. It's just, the physics is the free body diagram and setting up the two equations. It's also, I want you to point out that because these penguins are tied together, they're going to have the same acceleration in the x direction. And then by Newton's third law, these tensions are the same in magnitude, but opposite in direction.